In this discussion, I'm going to go over passive design. So we're going to go over what is passive design, what are the five passive design principles. So these are really important that you know all five of these. They all sort of work together to make a fully passive design. And then we'll look at some examples of each, how they work together to minimize any energy use, and then also look at a little bit about natural ventilation and a real brief history of some aspects of passive design. So passive design, and you want to jot this down, is utilizing surrounding conditions to reduce energy use. So really we're working with nature instead of fighting it. We build these big buildings, and really what we're trying to do is just control the environment. And by doing that, we literally wall it off. Okay, so we build these walls and then we actively heat cool. And so the idea behind passive design is instead of just like plopping down a building anywhere you want, any orientation, any size, put the windows wherever you feel like it, whatever looks nice, you know. Um, Instead of doing that, you want to think about what's actually going on in the space climatically. Where's the sun coming from? Where's the wind coming from? That sort of thing. And design your building to take advantage of those conditions. So how do you capture the most sunlight possible in the winter, but block it in the summer? How do you capture the prevailing breezes to cool the building off in the evening and then block it, when you want to keep it warm. And so that's the idea behind passive design is let's figure out what's going on around the building and use as much of that free energy as we can. I mean, there's energy pouring in, right? Like we have sunlight all the time, and we have these breezes, and even you can even get into like water management and so forth. But the idea is let's use the ambient conditions to reduce our energy use. So that's passive design. Now, passive solar design is really just the solar part of that. So how do we capture the most sunlight possible in the winter and then block it in the summer? And I want to distinguish that between active solar design. So passive means you're passively capturing the energy. Active means you're actively generating energy. So that would be like solar panels and wind turbines and geothermal and all of those renewable energy sources. So that there you want to be really careful about the difference there. So our five design principles, which we'll go each in detail here in a minute, are orientation, windows, shadings and overhang, insulation, air sealing, and thermal mass. So let's go over each one of these. Um, Very important to point out that if you want to have a truly passive house and maximize maximize the utilization of these ambient conditions, you have to use these all together. And this will make sense as we look through them. So number one is orientation. Okay, so of course you want to jot this down. So orientation is just which compass direction the building is faced. So we'll keep it simple. We're in the northern hemisphere, so we'll just deal with northern hemisphere. Just know that everything's flipped if you're down below the equator. So in the northern hemisphere, you want your building to face south. I think a lot of us know that intuitively, if nothing else. But the idea here is that you want the long ridge of your building should be faced south. You can see in this image, this is south, okay, and then you have north behind the building. And so the long east-west ridge should be faced south, and that is to capture the most sunlight. Um, and why is it south? Well, in the northern hemisphere, that's because the sun is almost always to the south of us. And I apologize, this is flipped around now. South is over here and north is over here. But you can see the east-west ridge line right here. So that's the long side. Um, and this is the sun path. Okay, so this is the sun path in the winter. It rises a little bit southeast, right? So here's south and here's east, so southeast. So it rises southeast, and then of course at noon it's almost directly south. It's not always directly south, but it's almost. And then as it sets throughout the day, it sets southwest, right? So here's west and here's south. So it sets to the southwest. So the entire day in the winter, as long as the sun's up, it is south of the building. Okay. And then in the summer, in northern the hemisphere and like where we are, and I'm recording this video from northern Delaware, which is about the same latitude. Yeah, same latitude as Philadelphia. And so in the summer, actually, the sun rises a little bit northeast. But by, early morning, it's going to be toward the south side or, east, southeast, and then, noon it's south. And then, of course, it's going to set the same, it's northwest. But it spends most of its time to the south. Now, this varies depending on how far north you are, but where we are and where most mid-latitudes, this is the general case. So the point is that if we want to capture the sunlight, we need to have our building face to the south. Okay, so that's orientation, right? So that's orientation. The second one, the second passive house principle is overhangs and shading. This is neatly summarized here. Keep the sun off the glass in the summer and let the sun fall on the glass in the winter. So you need to have windows on your south side, which we'll go over in a minute. But if you have windows, that's great because let's say you look at this building, right? So here's a simplified building and you have these windows on the south side. So that's great. You can let that sun in the winter. But the problem is if you don't have this overhang here, okay, you can see what this is. This is the sun angle. That's what these lines are, right? So this is the summer sun, right? It's high in the sky, so it comes from higher angle. The winter sun is lower in the sky, it comes from a lower angle like this. And then spring and fall are going to be in between. And so the key to an overhang is that it has to be designed just the right length so that it blocks the summer sun but allows the winter sun in. And if we sort of keep in mind that the sun is, of course, not in a straight line. So let's draw some more sun lines here, so to speak. Right. So if the sun's coming in at this angle here, right? Sorry, it's really hard to draw on this thing. So that the thing is, if this overhang wasn't here, and that's that summer sun, gosh, the summer sun would come in and hit the window, right? And the sun would hit the window, and the sun would hit the window, right? So by building this overhang out like that, it blocks all of that light so that only this sun comes through and you notice the sun does not hit the window. But then the winter sun, almost all of it's going to come in, right? So some of it's going to get blocked by the overhang, but a lot of it's going to come in the window. Okay. And that's the key to this is that you want to build those overhangs so that they're the right, just the right amount, so that it blocks that winter sun, or excuse me, blocks the summer sun, but allows that winter sun in. And the spring is kind of, spring and fall is kind of a wash. Like it's fine to capture sunlight usually. But in the high part of the day, it might block some of the sun, which could be good in the spring and fall. So you can accomplish the same thing with foliage, like a deciduous tree, right? So if you plant a tree right here, it serves largely the same purpose as long as it's a deciduous tree, not an evergreen. And so, in the summer, it drops its leaves. I know a lot more sunlight through, and then in winter, excuse me, in the summer, I think this backwards. In the summer, the leaves are there on the tree, and so it'll help block the sunlight. And then in the winter, it drops the leaves and allows the sunlight through. You can use things like vines that grow in the summer and go over an awning, that sort of thing. So you can get creative with this. But the goal is block that summer sun, allow the winter sun in. And you do that by having south-facing windows. And so there's some creative ways you can do this. It involves trigonometry, but with some work, it can be done. Right. So block that summer sun, allow that winter sun in, and make sure that it's south-facing. And third principle is having windows. Okay, so windows, you want to jot that down. Now these have to be used properly. So windows, obviously, the key to them is they allow sunlight in. And so if you have the windows on the south side, like you see in these images, and you can also see there's an overhang here, there's an overhang here. This has southern facing windows. Here's a big overhang on the porch. A little bit of an overhang here, but there's actually, you can see a little overhang here as well. And so all of these three really have to work together, and one just doesn't work without the other. If you have, your big south facing wall, but you don't have any windows, it's not going to allow that winter sun in. And then the overhangs, of course, have to block the sun from those windows. And so when you design a passive house in the northern hemisphere, most of the windows, most of the what's called fenestration should be on the south side, like you see here. These are really great examples. So you can see a whole bunch of windows here and here, ridge, south facing, long ridge line, right? And if this is designed properly, there would not be many windows on the back. There would be a limited number of windows. And the side is kind of in between, but you don't want to cover the whole building with windows if you can help it. Of course, some commercial building designs do that for aesthetics, but the problem with north-facing windows is if you remember from that sun path chart, the sun doesn't really hit the north side. I mean, it will a little bit in the summer, but that's really not important. The problem with the window is it's not a good insulator, and so you can think, well, why? I'll just throw windows all over the place, and that way, it allows as much sun as possible. Well, that's great, except that on the north side of the building, those windows are mostly just acting to lose heat. They're really just not capturing much heat, but they are losing a lot of heat because they're just not good insulators, and it's impossible to make them good insulators. The maximum R value for windows is something like R8, whereas you can get a wall that's R19, R20, 25, and so they're not good insulators. So you don't want them on the north side and less on the east and west. Okay, so pretty straightforward. Those ones have to work together. Here's just another image. This is actually a picture of I took some students to Denmark back in the day, and this is really cool. It was kind of like an Earthship type house or building. Sorry, it was sort of a sustainability energy training center, and you can see these big south-facing windows, and there's a little bit of an overhang here. And they used that. This was a passive house. This actually has a living roof, not even just a green roof, but it's dug into the hillside. And it's in Denmark, which is why these solar panels actually capture a pretty good amount of heat, even though they're kind of vertical, because that's pretty far north. But anyway, I thought this was really cool, and this building was amazing. It used almost no heat at all throughout the year, and it's a pretty cold climate up there. So that's the first three. So we have orientation, overhangs, shading, and windows. The third one, or excuse me, the fourth one is insulation, air sealing. I think this is really self-explanatory. If you want a super efficient house, you need to have it tightly sealed and really good insulation. Insulation prevents heat loss through the shell, and air sealing, of course, prevents leakage. So this is all pretty easy. You want to have something that's really well insulated, like something like this is no bueno. You want to have good insulation, something like this, which is an interesting use of fiberglass bats. But really good insulation and really good air sealing is very important. And all passive homes will have both of those. And then our last principle, you want to jot this down, is thermal mass. I think the first four principles are pretty straightforward and pretty easy for just about anyone to understand. And they're used in a lot of buildings. Less so the orientation and windows are to some extent, but of course the insulation and air sealing are. But they're pretty common sense. So thermal mass is a little bit different, and not a lot of buildings use thermal mass. So a thermal mass is anything, as you see here, is anything that material that takes a long time to heat up and cool down, right? So think of water. Water is a good thermal mass. Like if you have a pool that's not actively heated, okay, so it's not a heated pool. I don't know if you ever noticed this, but it takes a while for the pool water to heat up, right? So if you have like a family pool, like your neighbor does or whatever, my neighbor had one growing up, and we used to go over there, and I used to be confused because the water would be really, really cold, even though it was like really hot outside in the early part of the summer. And that's because it just takes a long time for that big, massive water to heat up. It's just going to absorb heat, sunlight, and it just doesn't heat up quickly. Now, there's also the element that there's some fresh water being added all the time, but overall, the water takes a long time to heat up. You could think of a pond or a lake or whatever, and it doesn't get like really warm right away. It can be blazing hot for weeks and weeks and weeks, and you go to a lake or a small pond, and like it's still cold. The water's still cold. That's because it takes such a long time to warm up. And then conversely, and again, I remember noticing this when I was a kid in my neighbor's pool. it would be like, cool in the fall, even the mid to late fall, but the water in the pool would still be really warm. And that's because not only does water take a long time to heat up, but it takes a long time to cool down. So it doesn't release that heat very quickly. And so water is just one example of a thermal mass, but any kind of natural earth material like clay, concrete's a pretty good thermal mass. There's certain thermal mass tiles. So the key to thermal mass and why it helps a passive house is the main thing, the main aspect. So look, if you see this floor, this is all a big thermal mass, right? So it's going to take a long time to heat up, and you can see the sunlight hitting it. And so if you integrate this with the first four principles, and you have this near a nice south-facing window in the winter, right? So now the sun's coming in through here in the winter. It's hitting this, and that floor, it takes a long time to heat up. So it's slowly, slowly absorbing that heat and just slowly warming up. So here's the key is when the sun goes down and there's no more passive heating happening, this floor slowly releases that heat. Okay, so it's going to slowly just release that heat, that radiant heat, all throughout this area and into the building. And so it's effectively like thermal storage for sunlight. And the sunlight comes in and it stores in the floor, and then it slowly releases that heat back out overnight when the sun's not hitting it, which then just keeps the house warmer overnight. And that's how thermal mass works. And in the summer, it's kind of nice because if any sunlight that hits this, it's not going to heat up very quickly. And so the floor will stay cool even though the rest of the room might be hot. Um, and so that helps mitigate the hot summer temperatures as well. But the real key is in the colder season, as this slowly heats up, and then it actually kind of is a natural heating source overnight. And thermal mass, there's a bunch of different materials. You may have learned about some of these in some of your architecture classes. But exposed concrete's a pretty good thermal mass. Anything that's stone or brick, rammed earth, you're gonna get into the earthship stuff, and then water, as I said. So cob, which is also went over in this lesson, which is mostly clay. Clay is a really good thermal mass, and so you can build whole houses out of cob, and then all the walls are like just big piece of thermal mass, and that'll help keep temperatures, sufficient. Just a side note, if you look at a lot of the old like Native American desert architecture, they always use these like 2 to 3 foot thick stone walls or adobe brick or whatever, so natural material. So those are thermal masses, and they knew that what with those thick walls, um, in the hot, hot summer sun, it takes a long time for that heat to travel through that wall, and it just kind of slowly absorbs it. So it's kind of like a natural heat absorption. Um, but then if you know anything about the desert, at night the temperature tends to drop. Even in the summer, it can be cool in the desert. In the winter, it can be really cold. And so as just as that those earthen walls absorb the heat and don't let it all through right away, they actually will slowly release the heat into the building, and they'll stay warm overnight. And so it just mitigates the temperature just like any good thermal mass. And so they were smart enough. They figured this all out over time. And as with a lot of these things, these are principles that we've almost like lost, because they used to use these they're pretty commonplace in a lot of places. So basically anything that's heavy and dense, and preferably with a rough texture, is a good thermal mass. But things like wood and vinyl and engineered flooring, carpet metal, these are all really bad thermal masses. And just another note, in this image you have a fireplace with a hearth, right? So you might be familiar with the hearth. So hearths are made of stone or some material like that, brick. And these are actually the thermal mass, and they're the reason they originally put hearths around these fireplaces. Think way back in the day before they had electricity and active heating and so forth. If a fire was your heating source, you would light the fire during the day, keep it going, and that heat would slowly absorb into all of this stone all during the day, and then at night you have to turn the fire down, you go to bed, and all that sort of thing. And then that stone would then slowly release that heat back out to the building. So that's another use for a thermal mass. And there's a couple of videos that you should watch. This one goes over a modern passive house, pretty interesting. Shows you how they install some of the materials. And then there's another one, sorry, about a more sort of like traditional design that you should watch as well. Now, another part of passive design is natural ventilation. And so, this is pretty straightforward. Um, you should design buildings and even whole neighborhoods to take advantage of prevailing breezes. So if you have a breeze that commonly comes this way, okay, so you see all these houses are facing that direction, perpendicular to that approximately, to capture that wind. And what you need to do, ideally have windows on both sides, as you see here. So windows on both sides. And then when you have a hot summer day and the house starts to heat up, but at night it cools down and there's a breeze, you open up the windows on one side, open up windows on the other side, and that actually cool it. Not only does it actively sort of cool the house, but it kind of siphons all that heat out and blows it, can pull it away from the house. Um, and so that's a natural cooling mechanism that you can use. Again, this is a passive design. This is not passive solar, it's passive design where we're using natural ventilation. And you can also use openings in the roof to naturally vent. We know that warm air rises. And it if you have something like this, so this is a picture that I took of a house in Denmark, and you see these all over the place in Denmark. They're really big on passive design there. And you'll see these windows in the roof. And it's kind of like what you would think of as a dormer on a regular house, but that's not why they're there. So dormers are just there for extra space as we build them. But these are actually for natural ventilation. And so what they'll do is that when it gets hot, they'll open these up, right, and allow the heat to escape through the windows. Now, sometimes you see windows all the way at the top, but the idea there is to use natural ventilation, sort of they allow the heat to rise because it's buoyant, and then escape through something higher. And they'll open the windows down here so it actually pulls air in and then goes out the window. Just as a pretty interesting aside, I was fascinated when I saw a lot of these houses in Denmark. This is made of a natural straw material, um, and they still build them some houses this way. It's pretty amazing. I mean, this is just a local, so almost like a weed that just grows in some of the swampy areas, and they harvest it. And it's this whole process where they dry it and they put it on there and they actually these big like sewing needles and they just kind of sew the roof together over the structure, which is there's beams behind this. But this is like a 1.5 foot thick. It's literally just straw, and that's insulation. It's also waterproof. It's pretty fascinating. You see this all over the place in Denmark, which was interesting. Um, and as I said, these are not new concepts. There's a couple readings in the Canvas shell this week that went over some of these really briefly. And this is Mesa Verde. This is in Colorado in the United States. This is a national park. You can actually go see this and visit it. And so this is actually carved into the cliffside. This is a south-facing cliff, and you can see a huge overhang. And also, they're using the south-facing principle, the orientation, to capture the sun. Um, whole parts, like parts of the city of Athens, like 2,000 plus years ago, were designed so all the buildings were south facing to capture that sun. There's a really interesting wind tower in the Middle East that they've been using for thousands of years, and that's where they basically allow the wind to blow through here through these towers, and it sort of sucks the air up through here, and it removes a lot of the heat. And here's a diagram that you can see the wind goes through here, it comes in and cools the building, and then actually pulls the heat out. Really interesting wind towers. And the Romans actually had a form of glass using volcanic rock, which is interesting as well. And so here's another video that you should watch. Really, really interesting design that uses cob, it uses straw bale, it uses all these passive design principles in a custom built home. Definitely worth watching. And when you watch it, just think about the role that cob and straw bale play, and which of those has the thermal mass and how that works. And also, which side of the building the cob and the straw bale are on. Okay, so that's it for the passive design portion of this content. And so hopefully now you have a decent idea of what passive design is, what passive solar design is. You should be able to describe all five of these principles. And then just some basic understanding. You don't have to memorize all of the old ways that they used it or who used it, but just have a general understanding of how this is not a new concept at all. And then also have some idea of how to use natural ventilation in a building. Um, and overall, just, you should have a good understanding of how you can utilize all of these principles to reduce your energy use in a building. Okay, that's it for this one.